So here's a simple example. I have a function. It takes two numbers, x and y, and it returns 1 if it's x greater than y, or 0 else. And here's how it works. Remember, RDI contains x, RSI contains y, and we need to put the value into RAX. So we use this compare Q, RSI, and RDI. Now, this is essentially comparing X and Y. Remember that if it was A and B, let me just go back to here, our compare instructions. Compare B and A is like computing A minus B. Okay, so let's go back. So this is my B and A. It's like, computing A minus B. And in this particular case, RSI contained Y. Do this. So this is what's contained Y, and this contained X, and this contained essentially X minus Y. But we are not changing any values. And then we look at when X minus Y. Then when I said, set greater A and L. Now set greater, then we can say that, let's look at here what this value was. Here's it's set greater. This is signed. And by looking at here, then you set the AL, which is the lowest byte of RAX, okay, when it's greater than 0. And then after that, we have this instruction move ZBL. This is it zeros the rest of RAX, and in this case EAX is again, like, this is my RAX, right? And the second 4 bytes, this is referred to as EAX, and this byte is set AL. So it's kind of, it assumed that this part was already 0 before, and in this case it zeros the rest of this by using EAX. And there are a lot of different optimization why it did not use RAX here, because sometimes it could use one less byte in encoding this into binary. And you should read the book to to understand why it's doing. But sometimes it's really so difficult that it's pretty impossible. Why do we have these condition codes? Because the condition codes allows us to make a comparison, and then when you do an if then else, then this requires that, right? And that is usually happens by what we call jump instructions. Okay, again we have JX, which is saying that this is a family of instructions, and what it does is the following. Now when you have a jump X, like in this case, jump, do this with jump equal, for example, to a certain address. I have an address here. And then you have two possibilities. So this is your code. When you're executing instructions, you move, linearly. You increment your address and you move on to the next instruction. Here, when you have an address here, which we call actually label, which is an address, then this label is here. So these are all instructions. This is the sequence of instructions. You execute them, execute. And when you have this, then you have two possibilities. One possibility is you can move on to here. This is one possibility. The other possibility is you jump here. And this is all depends on this condition, which is based on the condition codes that were done by the previous instructions. So here are our jump instructions. We have jump 1, which is unconditional. This is essentially a go-to. And then we have other things like jump equal, jump not equal, and etc. Okay, the same ideas. So here we have a conditional branch, and this is a case where I'm computing the difference in absolute value. I have X and Y. And if X is greater than Y, then the result is X minus Y. Else, result is Y minus X, and you return the result. Okay, it's pretty simple. You'll always returning a positive result. Now, when we look at the assembly code, and this is it may not be exactly the same thing, but usually we have this, this says that generate the assembly command. We apply 0 optimization, and then also other options. So you should be by the end of this course, you should be able to read the man page of the compiler and understand basically what these options actually work and what they do. So here's our code. We remember RDI contained X, okay, and RSI contained Y, and we compare them. Okay, this essentially, sets the condition codes. And then with these condition codes, so when we have this jump instruction, it uses the condition codes. It says .L4. This is like a label. Essentially, like in the assembly code, you don't see numbers, but when we look at this, this is essentially an address. And when you look at the binary code, you see it's 0x40 blah blah, okay, which corresponds to the address of the next one. So Mercy, when do these flags are reset? They're not reset. It's just that whenever you do, they are set, and that's it until someone else sets them. So the flags are never reset. So here, okay, we check for the jump less than or equal to. Remember, this is the reverse the condition. We were checking x greater than 0, and the reverse condition, reverse test, is actually x less than or equal to y, which is what we do here. And then if the reverses negative condition test is true, then we jump here, and then we move RSA into RAX, okay, which is we move y into that, and then we subtract RDI here, and then as a result from of this, so y equals y minus x, y minus x. Else, well, if this condition is not true, then you do this, and then you return at the end. So you can see how basically the jump works with these condition codes. Now, the way we understand is like, like in the bomb lab and in the rest of the lecture, we'll say that, we know that, C has a, GOTA assignment, and GOTA is very low level. So the way to understand this is we have this, here's a C code, and there's the C code, okay, with GOTO. And the way it works is we will write our assembly code in this C plus GOTO instead of using if and else. So in this particular code, like the corresponding the assembly code, I can, so it's like this, you have C, and then you generate the assembly code. But you take this assembly and then you basically have this C plus GOTO, kind of, you change it to go to understand this fully. So here how it works, you say that you do the negated test, just the opposite. Instead of greater than equal to 0, you say less than or equal to. If the negative test is true, then go to else, which is here. This is the label that we're talking about. And then you say result is y minus x. And then otherwise you drop here. And then when we are done, you say you go to done, and then you return the result. So this is how the compiler does the translation. Remember that I have this value, here's a test, the then expression, and then the else expression. And this is the go-to version. And then just basically, what's this then what differs from here is that the then expression, the test, the else expression, these are change from like code to code, but the general structure is this. So why do we do this? Because when you in the bomb lab, you will be seeing this assembly code. Okay, and in order to understand what they do, you need to map them back. You need to translate them back to kind of C code so that you can do this reverse compilation. Okay, back to C. Now, when we do this checking, remember, let me do this, execution here. So usually, your code is like a linear, sequence of instructions. And then once in a while, you have this, conditional, blah, blah, jump equal to, that's about L4. And then it moves here. And maybe, .L4 corresponds to this address, to this instruction. Okay. And it moves like this. Okay. So, and then then maybe we have an instruction like, compare blah, blah. Now you have two possibilities. Okay. One is after this instruction, you can go below, you just fall here and you just execute like, so this is possibility one. Okay. The other possibility, which I'll draw in green. Okay. After this, well, you may be jumping here and then executing these instructions and so on. So this is essentially, doing this. And now when we do this, these two are both okay, but sometimes, we will see this in detail in the upcoming lectures. the processor actually wants to read them into a pipeline. Okay, so when it's reading one thing, it's getting ready to execute the next instruction. It's fetching the previous, like, even the next one, and so on. So if I'm executing one of them, you want to see ahead. Okay, remember, like, think of this as if you're reading a book. It's usually sequential. You read page 50 and then 51 and then 52. Okay, and then at 52, what if there's a kind of link that they now go ahead and read page 100. If you did not understand this topic, for example, or if you cannot solve this question, then go to here. If you did, then you can just follow whatever the next. Then it will be problematic because remember, that you are photocopying these books, okay, depending in advance. And what you don't want is, you don't want to have, like, when you're here, you want to make sure that if it's everything linear, then you can photocopy all the pages and go home and then work fine. But what if there was this jump case? Well, if you cannot complete this exercise, then you have to jump to another place, which is not in your photocopy bunch, right? Then it's very risky. Okay, it's not nice. And this is the same thing happens with the processor. It wants to predict what the next instruction to be executed so it can get ready for it. Okay, and these conditional jumps are actually really bad because you cannot predict until you arrive at that junction, at that conditional jump. So sometimes it's unavoidable, but sometimes it is. And for this, the Intel has this conditional move instruction, and it's like the following. So imagine that, we have this code, you have this test, and then if it's true, then you do the then expression, execute, then you do the else expression. And what if we do the following? Like, what if we convert this instead of having this condition? What if we say, I will compute the then expression, I will compute the else expression, then I will do the test, and based on this test, I will return whatever it is appropriate. Okay, and then you return it. Now, in this case, there is no basically two possibilities. You'll be executing this one, and then this one, and then this one, and then the only condition is that whether you will be moving this eval into result or not. That's it. And then you will be executing this one. So this is really nice. If this was your book, then you'll be very happy. Now, why is this nice? It's nice because you don't have any disruption in the execution flow, okay? And, this is essentially supported in a post-95 x86 processors, okay? And this is essentially a move instruction, which moves between registers only when a certain condition is set, okay? And what's the downside? Well, the downside is I execute the then expression and answer expression before the in comparison. And that is kind of like, it may be a waste of time because, you do the computation and only after that you decide which one to take. So let's look at this particular example. In this case, it's the same code, except that now we use basically a different compiler option to use what we call this conditional move. So this is conditional move instruction. And what it does is the following. Again, you can read the rest, but here it computes the results, x minus y, and puts them into RAX. It computes the else portion. It puts it into RDX. Okay, so it does both of them. And then it says, and then it compares x and y. So it does the comparison at the end of the computation. And then it says conditional move RDX to RCX if less than or equal to. So what this is saying is, if it's less than or equal to, then you move from RDX into RAX. If this condition is false, you don't. Okay, conditional moves, it means that, move if test is true, and else, okay, not move, else. Okay, that's it. So this is a case where I have no basically disruptions in my execution flow. Note that, like this is not good for all the conditional moves. For example, if you have a expensive condition where it's like the then part and the else part, they are all very expensive, then it doesn't make sense because you're doing quite a lot of work here. So then, and the compiler tries to guess them, which one is hard and which one is easy, and then it uses the proper, basically, whether it decides whether it should use a conditional move or whether it should do with this conditional jump. Or sometimes you can have a risk computation. For example, remember that when we are doing this computation, like P, and you compare this with star P, which can be a null pointer access. And we said that we would prefer this sometimes because if P was 0, then basically, then I don't need to compute the second part, and that's why basically we may get some undesirable effects. Or sometimes the computations that I do with the then part and the else part, sorry, and the else part, they may have some side effect. Okay, so when I do this, I am kind of multiplying x with 7. It's changed. So it means that I cannot do them at once. So they should be side effect free. Only if these conditions are satisfied, then the compiler picks to use the conditional move in order to optimize the runtime performance. Okay. So now let's look at our how we can convert do while. Remember, like in our high-level language, we have this do while operator, but in reality, we don't have a do while instruction in our assembly. So we need to do this. So we will go into this example, which is we take a number x, an unsigned long number, and we will count the number of bits. So here's, if this is my x here, okay, and it has the number of say 0, 0, 1, 0, 1. If we have this, then we need to return the number of ones in it. Okay, and here's the code. You set the result to 0 initially, assuming there is no, and you take x. You end the bitwise end with 1, which is all zeros but 1 in the last one. Okay, and then you add this. So the result of this computation is a 0 or 1, and then you increment the result by 1, and after that you shift right by 1. Okay, and then that means that you discard that, and then you say while x. What this means is if the rest of the x bits are 0, then you quit. Else you continue until it's basically it's over, and then you return the result. So this is the C code, and what we will do is we will, like, instead of do and while, we want to do this with the goto version. Okay, and in a do while it's pretty easy. We set it to 0, and the computation is pretty easy. And then you just check the condition, and then say you loop, and then you go to loop back to here, and that's it. And then you return the result. And actually, as a matter of fact, this is the assembly code that we have here. You set 0 into EAX. Again, this is equivalent to RAX, and the reason why a compiler does this is probably it knows that it will not be using the remaining 8 bits, the remaining 4 bits, and that it's cheaper in terms of, for example, the binary encoding to store this. Okay, so don't worry too much about it. And then the RDI, this contained X. We put this into RDX, and then we end it with that. Again, EDX, this is like you can read this with RDX because I'm only focusing on the last bit here. Then you add RDX into RAX, which is this, okay? And then you shift X by 1. And when I shift this, remember here, this sets the condition codes okay, implicitly. Okay, and then I do jump not equal to dot L2. Dot L2 is the address here. Okay, and you move back and you do this, and then finally we return. Again, there is a discussion in the book why it uses rep and return, which is not conceptually thing, but there's a reason for this, so you should refer to the book. So if when it's doing this do while translation, remember we have do while, I have a test, and then I have a body, and the go-to version is, here's the body, if test, then go to loop. Okay, that's it. Now, how about how do we do this with the general while? Well, there are basically two different translations that the compiler may make, and this one is done with the jump to middle translation. This is translation number one. Okay, this is used with zero optimization. Again, here we have a test. Here we have a body. Now, the go-to version for this jump to middle translation is the following. You have the test here at the end, and at the beginning you do a go to test here. Jump here. You do the test, okay, and if test is true, then you jump to the loop and you execute the body. So the main difference in the while is that while doesn't guarantee you that it will be the body is executed at least once. Okay, it may execute 0 times, and this is how it works. Again, the best way to understand this is you should write these small C codes. You can just compile and then compile them to assembly and see basically how the compiler translates. Okay, that's the main thing. And so for this particular code, here's my test. Okay, and if X is then go to loop here. Okay, and here I have this go to test, and that's it. So that was the first translation. The second type of translation is what you call number 2 is the following. You have this while test body. Now what we do is we will convert this into a do while version. Okay, so here's the do while version, but before this we guard the entry by performing a non-negated test here. Okay, if the negated test is true, then you go to done. Else, you fall below and then you execute here. Okay, and with this, now I know that this portion, I know how to translate this. Okay, this portion, this translation is pretty easy, like this. Okay, all I do is I add it, I move this here. Okay, and I use the do while translation for the rest. Okay, so this portion is the guard, okay, which ensures that if the condition is not satisfied, the loop is never executed. Now, in this case, this is again the code that I have here. So this is the one that's doing the guarding. Okay, so this is the initial condition guard at the entrance of the loop. And what about the for loop? Well, in the for loop case, we have initialization. Okay, we have a test, we have an update, and we have a body. Okay, and for this case, I'm rewriting the same code here. So for I equals 0, and then the word size is essentially, we define this as 8 times the size of an integer. Okay. This is because this is size of integer, this is in number of bytes. Okay, and by multiplying this, then I will get the number of bits, okay, which I will be iterating on. So I go through them, and then I say I shift it by I, end it with 0, 1, and then you add it here. So in this case, the initialization is I equals 0 here. And then the test is I is less than, word size, and the update is this, and then body is this part. And what we do is, again, we do the same kind of thing. We know, how to convert while here. Okay, so you put an initialization, and here's the body, here's the update, and here's the test. That means that, this is, I put the initialization here, here's the while, and this is the update here. Okay, and that's how it works. And then we know how to translate the while version.